Hello everyone, welcome again. So today's lesson is on pH. So what is pH, how it relates to acidity, and how to calculate the pH. Okay, so that's what we're looking at. So what is pH? Well, pH is a measure of the acidity of an aqueous solution. So when we have a solution of water and something else, pH measures how acidic that water or whatever else is. In a neutral solution at 25 degrees Celsius, the concentration of the hydronium or hydrogen ions, okay, so basically let's just talk about hydrogen ions for now, has a value of 1 times 10 to the minus 7 moles per liter. Okay, so in water at 25 degrees Celsius, and it's neutral, it's not acidic at all, the number of hydrogen ions in the solution is 1 times 10 to the minus 7 moles per liter. Which equals the concentration of the hydroxide ions. So it happens that if you're neutral, the number of hydrogen ions equals the number of hydroxide ions. Okay? So the concentration of H plus is 1 times 10 to the minus 7. The concentration of OH minus is also 1 times 10 to the 7 moles per liter. Okay? So the solution will be basic when the concentration of H plus is less than this number. So if this number was, say, 1 times 10 to the minus 8, this would be a basic substance. Okay? So if H plus aqueous is less than 10 to the minus 7 moles per liter, but if the H plus or H3O plus is greater than this number, then the solution will be more acidic. Okay? So basically, if H plus was, say, 2 times 10 to the minus 7, then that would be acidic. Okay? So 1 times 10 to the 7 is neutral. Anything less than that, any less hydrogen ions, or hydronium ions, this guy, is basic. Anything more, so having more hydrogen ions, is acidic. Okay? Just that simple. So describing the acidity of a solution using concentrations with negative powers is cumbersome. Okay? So I certainly don't like using 1 times 10 to the minus 7 or 1 times 10 to the minus 8 numbers a lot. They're not very easy to use. Mathematically, they're quite painful to work with. So what we use is a more convenient approach. So we basically just transform the numbers or map them to a more sort of usable set of numbers, and then we just map them back if we need the true number. Okay? So basically pH is the way we map these hydrogen ion numbers from the real number to a pH scale, and then when we want to work back, we can just map them back the other way. So the pH, or potential hydrogen scale, is a logarithmic scale that indicates the concentration of hydrogen ions in a solution. Okay? So pH is a scale that measures, and it's logarithmic, that measures the concentration of hydrogen ions in a solution. Okay? That's all it does. Now, for those who are familiar with logarithms and maths, logarithms are just a way of condensing big or small numbers into kind of more usable forms. Okay? So if you can manipulate logarithms from mathematics, you will have no problem with this section. So as I said, we're talking about maths. Mathematically, the pH of a solution is calculated by pH is equal to minus log base 10 of the concentration of hydrogen ions. That's what it is. Okay? So that's the formula, where this bracketed H plus means the concentration of hydrogen ions in moles per liter. Okay? So whenever you see square brackets and then something inside, it means concentration in moles per liter. Okay, that's all it means. So for pure water, pH equals 7 at 25 degrees Celsius. Okay, so when you've got nothing in the water, the pH is 7 at this particular temperature. So as the concentration of H plus, remember square brackets is concentration, increases, the pH goes down. Okay, this is the bit that confuses a lot of students. If the acidity goes up, the pH goes down. Okay, that's just a result of the minus logarithm stuff. So just remember that. pH goes down, acidity goes up. Okay, so just don't get confused. Otherwise, you might write the wrong thing and then it means something completely different. So the pH of a chemical is less than 7, so 6, 5, 4, 3, 2, 1, then it is an acid. Okay, we consider it an acid. A pH of 7 indicates neutrality. It's not acidic or basic, it's just neutral. And a pH greater than 7 is just a basic substance, so the opposite of an acid. Okay? So the higher the concentration of hydrogen ions, so the more hydrogen ions you have, the lower the pH. Remember? Because more hydrogen means more acidic, which means lower, going down in the pH. Okay, so down. So if we look at some typical chemicals that you might see in everyday life, the acid in your stomach, which helps you fight off disease, is at pH of about 2, and it's hydrochloric acid. Hair conditioner is about 2 to 5, so it's acidic, surprisingly. Obviously soft drinks are acidic because they've got so much carbon dioxide in them, so they're at about 3 or 4 on the pH scale. Human skin is about 3 to 5 because it, again, is fighting off bacteria and things like that, so it's a bit acidic. Human blood is a bit basic, it's 7.4. Okay, so it's above 4, so it's basic, not very acidic. Seawater contains some basic salts, so it's about 8, so it's quite basic, not very acidic, in other words. Toothpaste has a lot of bases in it, so it's about 9 to 10. And most cleaning products are quite basic. And oven and drain cleaners, which is sodium hydroxide, are very, very basic, 12 to 14. Remembering that the pH scale goes from 1 to 14. So 2 is very, very acidic. 14 is really, really basic. It's the limit of basicity. Okay, so that's just something to help you kind of figure out what's going on. Okay, pH is a logarithmic scale, remember, as I mentioned. So a change in pH of 1 indicates a tenfold change in the hydrogen ion concentration. Okay, so this is a product of the logarithm again. Okay, so if I go from 1 to 2, or actually the other way, 2 to 1. So I had a substance with pH 2, and then I added hydrogen ions to be pH 1. I would have had to add 10, if I compare two things, pH 2 and pH 1, pH 1 has 10 times more hydrogen ions than pH 2. Okay, that's just how it works. Okay, that's the result of that base 10 logarithm. Okay, so pH 1, the very most acidic things, are super acidic, and 14 is the most basic things. So something with a pH of 1 has 10 to the power 14 more hydrogen ions than something with a pH of 14. Okay, that's a huge difference. Okay, so how do we measure the pH? We can do it a couple of ways. So measuring pH the pH can be measured, by using indicators or pH meters or pH probes. Okay, so that's just a probe kind of device. What you can do is you can use indicators. So if you've ever played with universal indicator, you drop some into the solution and it will change color. If it's red, it'll generally be acidic. If it's purple or blue, it'll be basic. This is how we remember it. And probes and pH meters measure the voltage of the cell formed in a solution and convert it to a pH reading. So because H plus and OH minus have sort of give the water or the solution a bit of electrical conductivity, or electrical properties, we can actually use those electrical properties to measure voltages. And then that voltage can then be, if we calibrate it effectively, can then be used to measure the pH. So that's a very smart way of dealing with the different, with measuring things. Because we can measure voltages and things very accurately, whereas colors are a little bit harder to distinguish, especially if you're colorblind. So indicators are not as good as digital things, digital meters, because we can measure things quite accurately digitally. However, of course, with any pro comes a con. It's quite expensive. Okay, pH meters are quite expensive to get. So pH meters and indicators tell us the concentration of ions in the solution, or they tell us the pH, which means one and the same thing. Okay. So this depends on the concentration of the solution, how many moles are present in each liter. So obviously, if you've got a more concentrated acid, it will have a higher pH than a less concentrated. It'll have a lower pH than a less concentrated acid. So that's dependent on that, and also the strength of the acid. So for instance, if you have an acid that is very, very strong, it will want to release all of its hydrogen ions. However, some acids don't want to release their hydrogen ions. So if there are no hydrogen ions in the solution, you can't actually get any acidity. So if it's a very weak acid, it will have very few of its hydrogen ions in the solution. Okay? So that will depend on the pH measurement. The pH measurement will depend on this. Okay? And the other one is the number of hydrogen ions per acid molecule that can be donated to the solution. So some acids can actually give more than one hydrogen to the solution, which means that they will have a lower pH than the same concentration and same strength of acid that only has one hydrogen ion that it can donate. Okay? And because a hydrogen ion is just a proton, we can consider a hydrogen ion to be a proton. So we say that something that gives off one hydrogen ion or one proton is a monoprotic acid. Pro meaning like proton, so that's kind of where that word comes from. And something that can give off two hydrogen ions would be a diprotic or two proton acid. Okay. Additionally, the temperature of the solution also makes a difference because it's related to energy. Okay, so how do we calculate the pH? We've talked about a lot of what it means or what it stands for, but how do we calculate the value? So if we have 0.1 mole solution of hydrochloric acid, then we have HCl goes to form H plus Cl minus. Okay, you can see that the H plus there's only one for every one of these HCl's, so we can call it a monoprotic acid. Okay, so it gives away one only because it only has one, and we assume that it's a very strong acid. So that assumption may not be valid for all acids, but for this one it is. And we say that it will completely ionize, which means that every single one of the HCl molecules will break up into a H plus and a Cl minus. Okay? So if there were 10 HCl molecules, when it's put in the water, there will be 10 H plus. Okay? So that says that the concentration of the HCl will be the same as the concentration of the hydrogen ions. Okay? That's key. Okay, so you got to remember that. So here's the symbols. Concentration of H plus is 0.1. Okay? The concentration is no different from the concentration of HCl. Then I'll write out the formula for you. pH equals minus log base 10 H plus. Now I just put this number in here and then smash it into my calculator. So there's the button log sometimes, depending on what calculators you have. It's just make sure you don't use log base E because that will give you a different number. So make sure you use log base 10. Okay? And then if you punch it all into your calculator, you'll get the answer to be 1. Okay, so the pH of a 0.1 mole per liter solution of HCl is 1. Okay? Fairly simple calculation. Now, for a diprotic acid, the hydrogen ion concentration will be double the concentration of the acid. It could be double the concentration of the acid if it is a strong acid. If it's a weak acid, then there's a bit more we have to play with, but let's just assume that it's a very strong acid, all of it ionizes. As each mole of acid can ionize to form 2 moles of hydrogen ions. So if it can give away 2 hydrogen ions, if each molecule can do that, there'll be twice as many hydrogen ions as acid molecules. One example of that is sulfuric acid, okay? H2SO4. When it ionizes, it gives away 2H plus a sulfate ion, okay? So you can see there's twice as many hydrogens as acid molecules. For a base, the hydroxide ion concentration can be calculated using the ionic product of water to find the hydrogen ion concentration. Okay? So we know that the concentration of hydronium, or H+, you can use them interchangeably, it doesn't matter, times OH-, okay? The concentration of OH- is always 1 times 10 to the minus 14, okay? So no matter what, it's always this number. So what you can do then is you can actually just kind of back calculate. If you have the concentration of this, you can always work out the concentration of this. Or if you have the concentration of this, you can always work out the concentration of this, okay? If you know this constant. Okay? So that concludes today's lesson on pH. Hopefully you've learned something about how to calculate pH. We've developed some mathematics to calculate pH. And hopefully you understand what pH actually is and what it measures. Okay, so it's just the hydrogen ions. That's all we're considering. Okay, so we'll move on to some questions, and hopefully you can reinforce that knowledge through some questions. So what does the term pH stand for? Well, we said it's not power of hydrogen or phenolphthalein. I didn't even mention this term. Periodicity of hydronium ions. It means none of these. It's about potential hydrogen. How much hydrogen can be found in the solution? Okay. So here's the statement. pH is a measure of the hydrogen concentration in a substance. Hence, it stands for potential hydrogen, which is the answer. What is indicated by a difference of 2 on the pH scale? So pH scale is logarithmic, remember? So the hydrogen ion concentration has changed by 100, or 10 squared. So if you change from, say, 3 to 2, that's 10 times different. Then you change from 2 to 1, that's another 10 times. So 1, 2, 3, going this way, that's 10 here. Then going this way again, that's another 10. So the total is 10 times 10, which is 100. Okay, and that's how we get our answer. Okay, the pH of an acid is not determined by which of the following. Okay, so whether the solution is concentrated or dilute, no, that's definitely true. That definitely affects the pH because it affects how many acid molecules we have. The atmospheric pressure above the acid, that's probably not, well, I didn't mention that, and I don't think that has much of a bearing because pressure doesn't really affect liquids. The strength of the acid, again, that has to affect it because that's how many hydrogen ions we can get out of the acid we have in the solution. Or whether the acid is mono or diprotic. So that tells, again, how many hydrogen ions we can get out. So it's probably B. So the pH is independent of the atmospheric pressure, and so B is the answer. Write symbols for the concentration of hydrogen ions and hydroxide ions. Okay, concentration of hydrogen ion is square bracket H+, and hydroxide ion is square bracket OH-. If I wanted the concentration of unicorns, I would just write square bracket unicorns inside. That's just what the symbols mean. Okay, so question 5. Which of the following equations most accurately shows the first ionization of sulfuric acid in water? So first ionization refers to the donation of the first hydrogen ion, okay? So when sulfuric acid meets water, gives off the hydrogen ion, the first one, okay? So it's probably not this one because this gives off 2 hydrogen ions. So that doesn't make sense because we said it's only 1, so it's not D. This chemical here is not sulfuric acid, so it can't be that one. So it's between these two, okay? Now, given that it's the first donation of the first hydrogen ion, we'd have to have some water available. So it's probably B because the hydrogen mixes with the water to give you a hydronium and this hydrogen sulfate ion. Okay, and that's your answer. For those who are confused, this is also true, except, and you could easily say this is true as well, but for the clarity of first ionization, it's better to have the water available so that you can see where each part is going. So this one is probably just not as clear, so we're going to pick B as our answer. Okay, but it's very, very close, and it's very hard to distinguish between the two. Calculate the pH of hydrochloric acid solutions of the following molarities. Okay? So here are the molarity being just concentrations. It's the fancy word for concentration. Here are the two concentrations. So if I punch the numbers in the calculator using the log button, it'll be 2. Okay? And if I punch this one, I can do it in my head, it's 3. Okay? Yeah. So if you punch the numbers in your calculator, you'll get those answers, I guarantee you. Okay? Just make sure you use log base 10, not log base E, because you'll get a different number and then you'll be confused as to why. So just use the correct log and you'll be no problem. Okay. So in an aqueous solution of H plus concentration equals 10 to the minus 6, calculate the OH minus concentration. Okay? The answer is 10 to the minus 8, and we get that by using that constant that I showed you. Okay. Remember that the concentration of H plus times the concentration of OH minus always is 10 to the minus 14. Okay. We know this is 10 to the minus 6. And so we get, if we divide this across, we get the concentration of OH minus is 10 to the minus 14 over 10 to the minus 6. And if we use our calculators, we get 10 to the minus 8. Okay. Okay, part B. The hydroxide ion concentration of water is 10 to the minus 4. Calculate the hydrogen ion concentration. Again, we did the same thing. So it's H plus times the concentration of OH minus, which is 10 to the minus 4. I'll just save some writing. And that equals 10 to the minus 14. Remember, we just multiply them together and we get 10 to the minus 14. So H plus concentration is 10 to the minus 14 over 10 to the minus 4, which is just 10 to the minus 10, which is your answer. Okay. So very simple calculations. All you need is to know how to divide, and then you're sweet. So that concludes today's lesson on pH. We've learned about what pH is, how to calculate it, and sort of what affects the value of the pH. Okay, so hopefully you understand all of that, and thank you for listening, and I look forward to seeing you at our next lesson.